This is a discussion of the summarizing questions from CR Activity 7 that were not addressed in the discussion during class time. So we'll just start right out with summarizing question 1. Describe the organization of the elements in the periodic table based on the protons in the atom's structure. So here's the full periodic table, but for this, I think it's probably more useful to use the reduced form of the periodic table with this structure picture that they gave you. So this is basically the top part of the periodic table here, all compressed together. So you'll notice that we only go through, well, it gives you the things in this part of the periodic table and this part of the periodic table just compressed together in this particular form. But as you work your way across the periodic table, number of protons, well, basically if you read it left to right, like you're reading text in a book, the number of protons increases by 1 in each of these. So hydrogen has 1 proton, helium has 2 protons, then we roll over to the next row. Lithium has 3 protons, beryllium has 4 protons, boron has 5 protons, carbon has 6 protons, and remarkably, up until a very high number, we always get a new element with 1 more proton in it. And this was some of the genius of Mendeleev to work with this structure and in fact even be able to predict things that he did not yet know existed just based on the pattern in the periodic table. So protons go up by 1 as you work your way left to right across the rows of the periodic table. And it is the number of protons that actually determines the identity of the element that you're talking about. So if I have something with 6 protons, it's always carbon. If I have something with 15 protons, it is always phosphorus. Then it asks us, describe the organization of the elements in the periodic table based on basic arrangement of electrons. Well, this is really what determines the columns that things appear in on the periodic table, or those groups. So you will notice, if you look at this, that everything in this first column, even though they have different number of electrons, and the electrons are shown on these electron structure diagrams as little dots, always has 1 electron in the outermost ring of electrons that are shown there, which are the energy levels for the electrons. So everything in this group has 1 electron, everything here has 2, everything here has 3, and those electrons are referred to as valence electrons. So things are clustered vertically by the common numbers of valence electrons. But the number of electrons also grows with the periodic table, because if an atom is in a neutral state, the number of electrons, which are negatively charged, is going to match the number of protons, which are positively charged. So here's 1 proton, 1 electron. 2 protons, 2 electrons, 3 protons, 3 electrons, etc. And so if you just look at the number of protons, you don't have to count dots on this particular representation. The number of electrons is always going to be the same. So electrons will also grow as you read the periodic table left to right and top to bottom. The third question, which electron's core or valence might have more power in predicting similar physical properties and chemical reactivity of elements in the same group? Explain your reasoning. Well, that is the valence electrons, because as we've talked about previously, it's things in columns that share the same properties as one another. And if you need verification of that, you should look at the form of the periodic table that has the element cards, and just notice that as you work your way down any column, they tend to have the same properties in the types of things they react with and the types of things they combine with. So it is the valence electrons that are sort of the magic for the arrangement of what combines with what, and they have more power in that. And in fact, that is basically the whole subject of activity 8, which is the next one you'll get to. Summarizing question 4. Positron emission spectroscopy, which is PET, is a medical procedure used to study the chemical processes involved in the working of healthy or diseased human brains. When using PET, molecules that our body normally use, like oxygen, water, and glucose, are labeled with isotopes such as 15O and 18F, and then injected into the patient. The PET scanner then records the signals that those isotopes emit as they journey through the brain. So in the space below, draw modified shell models like those used in exploration number 1 for 15O and 18F. Label them clearly. So this is hitting on the concept of isotopes. Well, the 15 and the 18 are the atomic mass, and the atomic mass is the combined number of protons and neutrons in something. So if I look at the quote-unquote normal version of oxygen here, oxygen has 8 protons and 8 neutrons, which collectively is 16. So normal is not the right word here, but the most common version of an oxygen atom that you would find in nature would have 8 protons and 8 neutrons. But oxygen 15 is not going to have that because it can only have 15 of these nucleons, these protons and neutrons together. So instead, what oxygen 15 has is, I draw my little nucleus, it is oxygen, so I can't change the number of protons, have to have 8 protons. But because protons and neutrons collectively have to equal 15, that means I have 7 neutrons, and neutrons are kind of the wild card. When you have an isotope, you might have more or less neutrons than the most common number of neutrons that you find in one of these elements. They don't give us any ionic charge on these isotopes that they're asking us to draw, so that means that the number of electrons is going to just be the same as a neutral oxygen atom, which here there's 8 protons, so there are 8 electrons, but those don't all fit in the same level. The lowest energy level can hold a maximum of 2 electrons, so there's the 2 electrons, and then you would put 6 in the next. It doesn't matter where in that ring you draw those electrons, as long as you have the number right. So there is my picture model of oxygen 15. Similarly, fluorine 18. I'm going to look at fluorine here on the periodic table. Fluorine, atomic number of 9, has 9 protons. The most common version of a fluorine atom you would find in nature would have 10 neutrons. 10 and 9 together means the most common atomic mass would be 19, but we're asked to draw fluorine 18, and so it's a very similar process to what you just did. Draw my nucleus. Fluorine's got 9 protons, and it has to have 9 protons to maintain its identity. But to be 18 collectively, that means this fluorine atom has 9 neutrons. And then I'm going to have 9 electrons because neutral fluorine is going to have the same number of electrons as protons. So I put 2 in my first layer, or my first atomic ring there, and then I would have the remaining 7 of those electrons in the next energy level, and that would be my picture model of fluorine 18. Summarizing question 5, we talked about at the end of class on Wednesday, and so if you were not in class and you want to catch the discussion of that, you should look at the Zoom recording for Wednesday's class.